right, so welcome everyone to FusionEPtalks, a student-led webinar on fusion science and technology. My name is Alexis, and I'm delighted to present our speaker, Veronika Klevarova, who will be telling us what she learned on the long and winding road of PhD, which took her to tokamaks across Europe and all the way to California. As a matter of fact, Veronika is one of the first people I met in the fusion community back at the Column Summer School in 2016. Then we met a couple more times along the way, and so I'm very excited to see her again on FusionEPtalks, where we try to cultivate such connections between scientists, engineers, and enthusiasts. She graduated from the European Masters in Fusion Science and Engineering Physics in 2015, and just recently obtained her doctoral degree in November. She spent most of the last few years between ITER and Aztec's upgrade, focusing on the root cause of disruptions. She's now eagerly awaiting the start of her postdoc at the Princeton Plasma Physics Lab, where she'll keep working on disruptions, and particularly on the development of DCAF, the Disruption Event Characterization and Forecasting Code. Today, she'll try to give us a sense of how much time it takes for fusion plasmas to collapse into a disruption, which, as you know, is a major threat to tokamak-based fusion power plants. Without further ado, I'd like to thank you and her for you all for zooming in today. I'll now mute myself and hand over to Veronika. Welcome and enjoy the talk.
Thank you very much, Alexis, for the very nice introduction. So yes, it's a pleasure to have the opportunity today to present the main results of my PhD research. So as the title suggests, we will be looking at the causes of the disruptions. The subtitle of my talk is that actually showing that we conducted a multi-device study of MHD modes in tokamaks in order to investigate their properties and to learn something more about them in the view of better preventing them in the future. So let's have a look at the little outline of my talk. Sorry, I will just try to remove, the outline of my talk. So firstly, we will recapitulate to ourselves what are and why to worry about disruptions in tokamaks in the first place. What do we need to know to prevent those events? How has this particular work contributed to the disruption prevention? And what can be done next in this context? So let me start. So disruptions, as you mostly know, induce sudden losses of the plasma confinement. They are happening on a timescale that is usually much faster than the plasma confinement timescale, so they are referred often to as quenches. In the triples, I'm showing a typical time traces that are to be observed during the disruption process. This is an example of a jet discharge that collapsed due to an MHD mode. What we usually see in the time traces is that we have a certain and very sudden abrupt of the temperature of the plasma. This is the phase that we call a thermal quench. This phase is shortly after followed by a collapse of the plasma current, and this phase is denoted as the current quench. Usually during the current quench, what is happening is that the plasma is also losing its stable position. So as I said, disruptions induce a sudden loss of the plasma confinement. The problem that is bound with those events is that the heat and plasma particles that are released can damage the confining vessel wall. There are multiple processes that can be damaging to the wall. Firstly, we can observe the sputtering of the wall particles, melting of the surface layer, and even penetration of the energetic runaway particles through the surface material. Plus, I shouldn't forget about the mechanical stresses that are applied on the vessel components. It is known that the larger the plasma current and the temperature of the plasma is, the more dangerous the disruption can become. So in the next step devices that will carry a high plasma current, such as ITER, it is absolutely essential to predict disruptions, avoid them, and mitigate them at last, in real time. So what do we need to know to prevent disruptions? First of all, we should know what are the causes of the disruption. And once we know or identify the causes, we should know the properties of the disruption predictors that are relevant for the real-time disruption prediction and forecasting. So what is already known to the community that an important cause of the disruption is an MHD mode that reaches a certain critical amplitude. Let me just briefly remind you that what already certainly you know is that the MHD treats plasma as a single electrically conducting fluid. The MHD theory can describe the destabilization and growth of modes. Some of them can become disruptive. And what has been learned in the past is that after reaching a certain critical amplitude, the mode can break down the plasma stability and induce the disruption. So once we have identified the frequent cause of the disruptions, which are the MHD modes, we might now try to investigate the properties that are relevant for the real-time disruption forecasting. First, we should know how should we look at and follow the evolution of the modes. The development of the modes can be followed by various diagnostics. The most ones are relying on measurements from magnetic coils. I'm showing an example hereby. This is an example of a jet discharge against that collapsed due to an MHD mode. Thanks to the magnetic sensors, we can follow the mode from the moment it got destabilized, then it was growing over a certain time period. Then it reached a critical amplitude and induced the sequence of the thermal and current quenches. The important information that we should know for disruption forecasting is first, the critical mode amplitude, and secondly, the time interval that separates the mode destabilization and disruption onset, here denoted as the mode duration. Recap, important information that we should know is the critical amplitude. And we are lucky that an earlier study yielded a formula for the disruptive critical mode amplitude. So we can actually use this formula and predict in advance with the scale, the disruptive amplitude. But what is problematic is the duration of the mode. In principle, the MHD can describe destabilization and mode growth in an idealized way. So this is the way that we can actually get an estimate of the mode duration. So we would follow the mode destabilization and growing until it reaches the disruptive scaled amplitude, let's say. But the problem is, as we will see, that the idealized description is often not in accordance with the experiments. And the problem is, furthermore, that the discrepancies are not fully understood. So in this work, it was aimed to provide new insight to the design of disruption forecasting and prevention algorithms. And what we wanted to do is to do this through the study of the MHD mode properties. There are two or even multiple, even more observations that are bound with the MHD modes. I denote them as key observations. Those observations are the following. So what we often see is that modes either rotate or are static, so-called locked at the disruption onset, and they can become locked after a deceleration period, or they can be Bohr locked. This is the key observations number 1, or A. The second observation that is important is that modes get destabilized at various plasma conditions. This has motivated introduction of the sort of disruption classes in the past. Those key observations might determine the action within the disruption prevention. In principle, this is the scheme that we might follow. During the discharge in real time, we observe the mode. We know the key information about the mode. We send this information to the disruption predictor, which is an algorithm that tells us if the disruption is likely to happen. And then the information processed by the disruption predictor is then submitted to the plasma control system that then takes the action. Either it tries to avoid the disruption, or ultimately, if the disruption is inevitable, it mitigates it. So here it was aimed to provide new insight in the properties of the disruptive MHD modes. In particular, two research topics were followed and investigated. So firstly, a previously derived model for mode locking was validated. The approach that we adopted was a comparison of the experiment with the predictions of the model. And secondly, we investigated the locked mode pre-disruptive durations and growths. In this case, we adopted the approach of reporting on phenomenological observations and usage of empirical formulae. As a working tool served a newly assembled large database of disruptive discharges. And for this database of discharges, manually noted were the two key observations that concern the mode movement and the disruption class. Let me state quite a few information about the database itself. So it comprises 4 devices of various plasma size, and the total number of entries is about 1100. Multiple devices of various plasma size will allow us to study the disruptive modes under a quite broad plasma parameter range, which was actually motivating us to include those 4 devices in the database. We applied common criteria for the database compilation. Those common criteria were observed across device. We can maybe talk about them in the discussion section. Here I'm just stating in a symbolic way what was actually followed during the database compilation. And the key observations that concern the mode movement and disruption class were manually noted for each database entry. So now we can jump into this research topic number 1, which concerns the mode rotation and the validation of the mode locking model. Let me first start with a couple of words about the mode rotation. So it was shown in the past that the rotation of the mode can stabilize it and thus prevent it or even postpone and prevent the disruption onset. So what we actually want in general is that the mode rotates because it represents a desirable mode property from the disruption prevention point of view. But what can happen is that under certain circumstances, an initially rotating mode can decelerate and lose this stabilization. It was shown that the lock-in mechanism is bound with the mode physical dimensions, its width. And in the context of the next slides, I should introduce 2 important terms. This is the first one is the locking duration, which is the time that separates the initiation of the bracking and the time at which the mode becomes locked. The second term is the mode locking width, a critical mode width at which the locking happens. So let me introduce the mode rotation in the context of the disruption avoidance. What we often see prior to disruption is the following scheme. So we have a rotating mode, then it becomes locking, or it undergoes deceleration, it becomes locked, and then we observe a disruption. So in principle, if we detect a decelerating mode during the discharge in real time, and we submit the critical information about the locking duration and mode critical width to the plasma control system, the plasma control system might take an action. It might try to induce the mode re-rotation, or it might try to prepare for an upcoming locked mode. A good thing is that the critical parameters, the locking duration and mode width, can be the critical mode width can be in principle derived conveniently in real time by a known model for mode bracking. And what we tried to do here was to confront the model predictions with the experiment. So let me please introduce the working equation. So in general, the mode equation of motion comprises of all forces that are applied on the mode. Here, in the model that we adopted in our study, we were considering just 2 force terms. One force term was accelerating the mode, and the other one was decelerating it. I'm giving a more specific formula in the at the bottom part of the slide, but let me stay with the symbols and let me just shortly describe what the symbols are representing. So the first term is about to restore the mode of the the motion of the mode through the perpendicular viscous coupling. So we can picture it in a way that we have 2 layers, one is rotating slower, one faster, and through the friction, the faster layer is about to enhance the motion of the slower layer. On the other hand, this force term incorporates momentum confinement degradation with the increasing mode width. The momentum confinement time is an important time scale that is capturing the momentum redistribution rate. The decelerating force term is actually bound in the electromagnetic interaction of the mode with the resistive wall. As this interaction goes along with the increasing mode width, the mode gets decelerated. There are 2 possible scenarios that are implemented in the model. They are bound with the mass that is undergoing the bracking. First scenario is such that we have a mode that is decelerating and the full plasma bulk is decelerating with the mode. The other scenario is another extreme, that we have the mode that is completely decoupled from the deceleration or from the movement of the plasma bulk. As I said, the 2 scenarios are extreme, and we can expect that the reality is likely somewhere in between them. In any case, integration of the mode equation of motion for given experimental inputs can yield the locking duration. And furthermore, point of locking bifurcation that is embedded within the model can give us the critical mode width for locking. So what if there is a missing decelerating force? And I'm saying this because in the future slides, we can see that we actually observe this. So let me introduce it shortly here. This is the case that is showing that we have an experimental data and the model is widely overestimating the locking duration. So we can approach this problem in two ways. So we can modify the mode equation of motion as we have it. We can force large momentum losses through the viscous force term, or what we can do in this case is that we increase the wall force term by a certain multiplication factor. The multiplication factor is an indication of a missing decelerating force. It is not carrying a physics meaning. So in our study, we compared the predictions of the model in terms of the locking durations and the critical mode width for locking in more than 100 ASDEX aggregate initial rotating modes. Now we can look at the results of the comparison. So first, let's focus on the cases where we observed an agreement. It was in about 15 out of the 100 cases. There, the modeled rotation variation reproduced quite well the experiment, plus the predicted drop in the momentum confinement time agreed quite well with the experiment. I'm showing here an experimental or comparison of the experiment versus the model predictions. What we can see is both the coupled and decoupled scenarios are reproducing the experiment. Here I'm showing a rotation profile of the across the plasma, and with the mode with increasing progressively towards in time. And what we see is that we are confirming our expectations, such that we are observing a sort of compromise between the two extreme scenarios. So we are not observing a completely decoupled movement of the mode from the, and we are neither observing a completely coupled movement of the plasma bulk with the mode. So we can actually estimate the locking durations somewhere between the two extrema that are given by the model. Out of those 15 cases, we extracted some rules of thumb that help us to say when the model applies well. Since when there is a certain relationship between the momentum confinement time and the experimental locking duration. In the experimental locking duration is embedded the mode growth rate. So we can think of it in the way that if the mode grows on a sufficiently slow time scale that allows the momentum to be redistributed across the radius, the model can apply quite well. What we also see, what we saw actually, that this model applies quite well for certain disruption classes. However, we had a bunch of problematic cases. In a number of discharges, what happened was that neither of the scenarios was in agreement with the experiment. We observed indeed a missing braking force. We could actually match the locking durations, but only at the expense of a drop in the momentum confinement time that was unrealistic. So what we think is that we must miss some ingredients in the model. Furthermore, let me state that we compared the theoretical mode width for locking with the experiment. And the problem here was that the modeled mode width systematically overestimated the experiment by a big factor, in particular by a factor at least of 2. So what we tried to do was to identify in a bit more systematic way the problematic cases. So we obtained the multiplication factor through which we increased the wall force term for all discharges, for all 103 discharges. And I plot them here. I plot the multiplication factor against the experimental locking duration and critical mode width. What we can see is that there is a region of the multiplication factor that is showing that there is no need for its usage, so when it equals 1. There is a tail of modes that are systematically falling in certain disruption class, and these are the modes that are large in dimensions and of extended experimental locking durations. What we actually also see is that the problematic cases are located systematically in the density limit disruption class. So what we did is that we extended the model, and we did the extension in a way that it took into account the variation in the plasma density. And what happened, or what we observed, was that the density this manipulation yielded then better predictions of the model. So let me summarize this first research task. So a previously derived model for mode locking was hereby applied on a large database of Aztec's aberrate initially rotating modes. The model can estimate critical information for the disruption avoidance algorithm, that is the locking duration and the critical mode width for locking. What we saw was that in case of large modes that were locking over long temporal interval, the predicted and experimental locking durations matched. Systematically, we saw that in high density disruption class, there was a missing bracking force and a modification of the mode equation of motion that accounted for variation of the density improved the model predictions. What we also saw that the theoretical mode width for locking systematically overestimated the experiment. So we made a couple of simplifications when deriving the formula for the mode width for locking, and those simplifications made probably or were the cause of this large discrepancy. So what can we do next immediately is try to reduce the simplifications of the formula for the mode critical width, and we can try to further search for sources of the missing bracking force. So let me jump into the second research task. This one was actually looking at the properties of the locked mode. Let's have a look at the locked mode in the context of the disruption mitigation. So let me state that in the large devices, locked mode is actually the most frequent disruption prerequisite. We can recall the usual pre-disruptive scheme, and we can focus on the final phase when we have locked mode that induces disruption. And for the moment, it is not important for us if the mode underwent a series of deceleration or it was born locked. So in real time, in principle, if we detect a locked mode, the plasma control system might try to do several actions. It might try to cure the mode, thus to try to prevent to reach the critical mode width. It might try to initiate a discharge shutdown through fast decrease of the plasma current, or if the disruption is inevitable, it can try to induce, or it can induce the fast plasma radiative collapse through inducing a sort of controlled disruption. So the, sorry, I can't see, yeah. So the disruption predictor should estimate what time is left for the plasma control system to take the action. And in fact, this time interval might determine the action to take. So the question that we might ask is, once we detect the locked mode, how much time is there left before the mode amplitude reaches the disruptive amplitude? So the question that is related is mode duration. Let me return a bit to the fact that we can estimate the critical mode amplitude thanks to an already known formula. We might use the MHD first principles to describe the mode destabilization and growth, which might give us the duration. This is what I mentioned at the beginning of my talk. But the problem is that the idealized description is often in disaccord with the experiment. Here I'm showing two experimental time traces from the Aztec's upgrade tokamak. The current quench is denoted by the vertical red line, and this is the evolution of the mode amplitude. What we see is that the amplitude very often fluctuates. And the problem is that we don't understand fully the origin of the fluctuations. If we don't understand it, then it's difficult to get it embedded in a model. So here we studied the mode duration within a multi-device approach, and we wanted to search for the source of the fluctuations, identify the factors that are determining the duration, and ideally it would be great to capture some basic parametric dependencies, so we would know what does the duration depend on. So let's have a look first at the factors that determine the duration plus the origin of the fluctuations. Here I'm showing the basic trend that we captured owing to the multi-device study. This trend is showing that we are observing larger durations in larger devices. In the plot in particular, I'm showing the median of the duration as it increases with radius. What is actually important, and it is denoted by the stars, is that the duration spans several orders of magnitude in all devices systematically. We might ask what is causing this large span. An immediate answer to this would be that each database pertaining to each device is populated by entries that belong to distinct disruption classes, and those are known to develop on a shorter and longer timescales. So we might sort of understand the why do we observe such large span. But what is in fact determining the duration? In the research, we addressed a couple of factors that could be determining the duration. We looked at the preferential discharge settings per device or even experimental campaign, effect of the wall material. Those are 2 points that were also discussed in the search for the origins of the fluctuations. And also we speculated, or not speculated, but we looked at the emergency discharge shutdown strategies. How do they influence the mode duration? And more are certainly to be discussed in the future. The problem is that this is a set of technical and physics aspects that make the cross-device interpretation of this trend quite difficult. So we wanted to also capture the basic parametric dependencies of the duration with the plasma parameters. So we performed a regression analysis and we obtained a scaling formula that is dependent on several plasma parameters. I'm showing the predictions versus the experimental points in the left plot below. What we can see is that the predictions actually suffer from uncertainties. Those uncertainties are possibly due to the reasons that were mentioned on the previous slide. On the other hand, thanks to this scaling, we can estimate the duration possibly in real time. And we applied this scaling for an ITER discharge scenario, and the scaling yielded an estimation of the duration of hundreds of milliseconds. So now let me focus on the last topic discussed in this talk. That is the pre-disruptive mode growth. So now we can actually estimate the duration and the critical mode width with scaling formula. But the problem is that we still don't know how the mode will grow towards the disruption. And this is quite important because the plasma control system might determine its action based on how much amplitude is actually left until the amplitude grows to the one that is about to disrupt the plasma. But let's recall that the modeling of the mode growth is difficult, specifically not restricted to the occurrence of the fluctuations. So we might try to twist the problem and ask ourselves how many modes reach certain fraction of the disruptive amplitude at a fixed time before the disruption. And we might try to project the information that we learned to ITER with the plasma main radius. So to do this, we adopted the multi-device approach here. So we asked ourselves how many modes reach a certain fraction of the disruptive amplitude at a fixed time prior disruption. As the fixed time point, we chose 10 milliseconds, which is a typical reaction time scale of the plasma control system. And as a working instrument in this task served the time to disruption curves that I will show on the next slide. Here I am showing a plot that is about to explain what is the time to disruption. It's a pretty simple complex, so it's a pretty simple concept. So now what we are observing here is an experimental time trace of a mode amplitude captured in the Alexis device. So we see here that the mode caused a disruption at a certain point, and we refer to this point as a reference point. And then we ask ourselves and look at which time before this disruption or before this point, a certain level of the critical disruptive amplitude was reached. So for the 50% time to disruption, we would look at half of the disruptive amplitude, which would be here. We would actually read this point on the time axis, and then this would be our 50% time to disruption. So we did this exercise for all database entries, and we were referencing here to the disruptive experimental mode amplitude. We collected all those times and we plotted them in one summary plot in the so-called time to disruption curves. This is a quite busy plot. I want to actually refer to point your attention to one particular point, which illustrates on how we might read the information from it. So this is a star that is pointing to 50% of the disruptive level in the compass device. So once we actually select a point, we can read from the vertical axis that about 70% of the disruptions reached at least 50% of the disruptive amplitude about less than a millisecond before the disruption. So what we were interested in was the cross-section of this plot at the 10 milliseconds, the typical time scale of the plasma control system. The plot is shown here. We might focus on one of the points and say that in more than 95% of the jet entries, the half of the disruptive amplitude was reached at the 10 milliseconds. What we can observe is the trend. The trend is optimistic with minor radius towards ITER. But the problem here is that we know only the disruptive mode amplitude after discharge. So what we did was that we repeated this exercise, but this time we were referring to the scaled disruptive amplitude. So once again, we retrieved the time to disruptions. This time we were referring to the scale disruptive amplitude. And again, we collected all the time to disruptions and constructed the time to disruption curves. And yet again, we were looking at the cross-section at 10 milliseconds. Let me comment on one particular point here again. Here we can see that about 88% of the jet entries reached at least 50% of the scale disruptive amplitude at the 10 millisecond before the disruption. Again, the trend is optimistic with minor radius towards ITER. So let me please summarize. So we studied locked mode pre-disruptive growth and durations. Those information are important for the plasma control system in the scope of the disruption mitigation. And we studied those quantities within a multi-device approach. We observed that the median of the locked mode duration increased with the plasma minor radius. And we also observed that the mode duration spanned several orders of magnitudes in all devices. We discussed a couple of aspects that could determine or influence the duration. They are a combination of technical and physics aspects. A newly derived scaling for the locked phase duration was applied to an ITER scenario, and it yields the estimation of hundreds of milliseconds, which should be a sufficient time interval for the disruption mitigation action. In JET, about 90% of the database entries developed at least half of both experimental and scale disruptive amplitude at the typical time scale of the plasma control system. The trend is optimistic with the plasma minor radius for ITER. So what we might expect here at this point is that in majority of the disruptions in ITER, the mode will grow at least to this level of the disruptive amplitude, which might be a message such that the mode amplitude might be a reliable parameter in the disruption prediction algorithms. As an immediate outlook, we might think of searching for origins of the fluctuations that we observe in the mode amplitude. And this might provide an input to the modeling of the mode amplitude in the future. So disruptions represent a sudden loss or incorporate a sudden loss of the plasma confinement, and they represent a major threat to future large devices. Here, we used a newly assembled large database of disruptive discharges. We collected it in 4 devices of varying plasma size, and we used it to study some of the characteristics of disruptive modes in the view of the applicability of the observations in the disruption predictor or plasma control system designs. We observed and followed the mode amplitude from the mode onset through bracking until full locking and the disruption onset, which is a sequence of events that is also foreseen there. In particular, here we confronted the predictions of a model for mode bracking with the experiment, and we looked at the locked mode pre-disruptive durations and growth. What can be done next is that we can, for example, study development of other plasma parameters that are important in disruption precursor phase, such as the plasma density, which might eventually extend the disruption prevention period. And we can use this database as a working tool in this task. So thank you very much for your attention.
Thank you very much for the very informative and good presentation. I see a question from Fabio Federici. I'll ask to unmute. Go ahead, please.
Hello, can you hear me?
Yes.
Okay, thank you for the talk. And I have a couple of questions. Maybe it's kind of a silly one. I didn't really grasp what is the physical meaning of the critical width of the disruption.
Mm-hmm. So critical width, so we are talking of critical amplitude in one case and critical mode width for locking. These are actually two different, they are referring to the mode amplitude and its physical dimension, but we approach them in 2 different separate topics. So in the first one, we were looking at the critical width at which the mode undergoes bifurcation during the locking process. So it actually decelerates abruptly to a lower, let's say, energetic state. This is, according to the model, captured analytically, and there exists a direct analytical formula that is saying that at this island width, W equals blah, 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 we observe a bifurcation. In the second task, actually, it was meant, or what was meant by the critical amplitude was the amplitude that is expressed by milliteslas, let's say, as it is captured by the magnetic coils in real time, let's say, during the discharge. And there we were referring to a point where it induced the disruption itself. So it can still be one mode that is undergoing deceleration and then disrupting the plasma. But there are two critical points from the point of view of the disruption prevention. This is the moment when it gets locked, so it's losing this stabilizing mechanism due to rotation. And then there is the moment when it actually induces the disruption. This is the ultimate point where we should worry about the most.
Okay, and if you go back, I can go back to page 2023, I think.
Mm-hmm.
It is quite a characteristic shape. You know, it rises and it goes down again. And I mean, if you have like a physical explanation on why you have that profile shape of the amplitude, and also the 50% looks quite close to the tip, so meaning that you have like if you have like a if you have like a span, so they can be a bit lower or a bit higher. Of that 50% seems a bit bad as a threshold. I would have used a little bit less to capture like. To be sure to capture all of them, rather than we would have used like 40 or 30%.
Mm-hmm. Well, the usage or the choice of the actual level of the disruptive amplitude can be made, of course, in the future. Here it was more to study the times themselves and to capture then the distinct levels at in the time to disruption curves. So if you would be then tuning the disruption predictor, let's say, you would certainly be searching for the most appropriate levels of the disruptive amplitude. But here I was talking about the 50% for the purpose of illustration and for the definition of the time to disruptions. It's close to this tipping point indeed, but this can be a coincidence. In fact, we have plenty of cases where the 50% was actually not preceding any tipping, or it was well, this is just an example. And yeah, well, you were asking also why do we observe this decreasing?
Yeah, why it is rising and decreasing again and then it disrupts?
That's the difficult question, actually. So what can happen is that simply the mode decreases in amplitude. It actually moves out or in distance from the magnetic sensors. This is an ASCII-X upgrade discharge. What happens often here is that the mode gets re-rotate quite often. So it is still captured by the locked mode detector, but it is rotating. So the amplitude that is captured by the sensors sensitive to the locked mode are not seeing the full amplitude. What could also happen, this is a bit speculation, but we have looked at this briefly as well, is that often we observe minor disruptions before the disruption, especially in JET and ASDEX upgrade, they are quite frequent. And there, what we see in the time trace is that we see a minor disruption. So we see the drop in the temperature, current spike, and so on, and then it is followed by a period of the decrease of the amplitude. So we are thinking that this might be sort of relaxation of the mode amplitude that is bound with the minor disruption. But why is this actually happening? And for example, if I would return to this case, there are much more fluctuations, and here they are even happening on very fast time scale. And I think that the origin of these fluctuations is not very, very clear at this moment.
In the meantime, could we go back to the scaling law? I was curious about something.
Mm-hmm.
So it looks like, I mean, that's just a wild guess from somebody who studies a completely different problem, but there seems to first be like a pretty big influence on the size, from the size in there. And what, how would you explain the fact that, I mean, okay, at least in terms of duration, the larger tokamak seem to be pretty much at the same place, at least in log scale. But compass seems to be really spread out over 2 orders of magnitude. And how would that, what do you think is the main factor in there for uncertainty?
Well, yes, sorry, what was actually the first? Yeah, you said that there is an influence with the plasma size. Indeed, actually, in the scaling itself, the factor that is showing or indicating the weight of the minor radius in the scaling formula is very strong. Compared to the other parameters that are in the scaling, this is the strongest one. Why there is such a why there is an observable discrepancy in between the devices, this is not very clear. No, I'm afraid that I can't answer your question at this moment.
Okay, I understand there's a lot going on in such scaling laws. And
hi, can you hear me?
Yes. Hi.
Hi. Thank you for the talk. I have a question. I think I missed a graph on a slide 14, top right. I didn't fully get the color codes and what exactly are the lines. If you can return back and explain it to me a bit. Yep, there is some two different lines.
Okay, so you are referring to the rotation profile.
Yes, indeed.
Okay, so this is the evolution of the the rotation profile in time. Indeed, we are observing this variation in the rotation across the plasma radius in about window that takes, I don't know, 130 milliseconds. So we are starting from a quasi-stationary phase, let's say, of the discharge, where we were observing the mode that was having a quite, let's say, stationary frequency. And then this is actually pointed at the 3.52 seconds. If we look at the plot on the left side, this would be this actually point.
Veronika, can I directly ask a good question? Each line is 10 milliseconds different step?
Should be. I should calculate them, and we would then see if this 10 milliseconds fit. But it depends on the time resolution of the viewing diagnostic. So I think this should be something like 10, 12 milliseconds, something like this.
Yeah, I mean, if the bottom is 3.65 and the top one is 3.52, and each line represents some interval, the time interval slice, then okay, it's roughly 10 milliseconds, and a color code.
And the color code is just for better orientation in the plot. So it just red is exchanged with blue. So it's red, blue, red, blue, red, blue, red, blue.
Okay, this confused me a bit.
Yeah, sorry.
No problem. Thank you. Very nice talk.